All right, chemists, today we're going to do some practice equilibrium problems. Here's an example of a chemical reaction that is all in the gaseous state. Now remember, it has to either be gaseous or aqueous. If you see anything that is liquid and solid, you just ignore that in equilibrium. Just leave it off. These are all gases though. So at equilibrium, the concentration of H2 is 0.040 molar. The concentration of I2 is 0.040 molar, and the concentration of HI is 0.32 molar. This is in a 2-liter flask, which we don't have to pay attention to yet because we already were given to it in molarity, M. That's moles per liter. This particular set of circumstances is unique to 400 degrees Celsius. So let's first figure out what our K value is. The equilibrium constant, if you remember, is products over the reactants. And they're going to be raised to the coefficients from the balanced chemical equation. So this is going to be concentration of products and in this case, the coefficient for HI from the balanced chemical equation is 2. So it will be HI squared over the concentration of the reactants multiplied by each other. This is our equilibrium constant expression. Now, if we want to figure out what the value of the equilibrium constant is, we will input these numbers. The key is you have to notice that it says it's at equilibrium. So I'm going to plug in 0.32 squared, 0.040 times 0.040. Plug that into my calculator and I get a value of 64. For our purposes, this is a number that does not have any units at this point in our chemistry career. The number 64 means that there is more products than there are reactants. So this is a particular reaction that is said to favor the products. Now let's go down here and see what happens if we disrupt or disturb the equilibrium by stressing it. The type of stress that we're going to add is going to be increase the number of products. So the type of stressor was, I'm going to add 0.15 moles of HI to the reaction vessel. Once we indicate that we've disturbed equilibrium, or you're said it's not at equilibrium, you know for a fact that you're dealing with an ice chart. So let's just put our chemical reaction down here. And if 0.15 moles are added to a 2-liter container, then my increase in molarity is 0.075 m. So you're also going to see this called a rice chart. All that means is the reaction is put in right there. So our starting values for H and I did not change. They're 0.040. But our starting value for HI did change. It's going to be 0.32 plus 0.075 for a starting value of 0.395. Now, in this particular case, we know which ones are going to get the minus because we added extra HI. Le Chatelier's principle tells us that it's going to shift towards the reactants. And therefore, the change is going to mean that we're going to add some more reactants and remove some products. Balanced chemical equation coefficients, then X. Sometimes to figure out which one deserves the negative X, you have to look at the value of K. In this case, K is 64, so it's greater than 1. That favors the product. Sometimes that can give us clues as to which get the negative. But the clue here is the fact that Le Chatelier's principle tells us that if you add more product, it'll shift towards the reactants. So the equilibrium concentration of these guys are going to be the same because every time you produce a molecule of H2, you'll also produce a molecule of I2. And this is 0.395 minus 2x. So now I'm going to plug it into my K expression. My K expression is HI squared over H2 I2, like such. Let's now plug all of this in. We know that equals 64. So now K becomes 0.395 minus 2x squared, 0.040 minus plus x, 0.040 plus x, like such, equals 64. Now, if you're looking at this and saying, wow, that's going to be a complicated math problem, I'm going to have to FOIL out, blah, and have to solve for x and all that. At this stage in the game, we're not going to do complicated problems like that. You have your calculator that'll help you. So we have to recognize patterns of numbers. So I'm not going to give you ones that are going to be super complicated math problems. So you can recognize something that's going on here. Like such. Now, to make this an easier math problem, I can take the square root of each side. So 0.395 minus 2x, 0.040 plus x equals 8. So now this is not as complicated. So I'm just going to algebra this out. Now I have a value of x as 0.0075. Let's go back up and plug that in. So x equals 0.0075. So the concentration of HI is going to be 0.395 minus 2x, or 0.38 molar. The concentration of H2 is equal to the concentration of I2, and both of those are going to equal 0.040 plus x, or 0.0475 to 2 sig figs, it would be 0.048 molar. So with that one problem, we walk through how to get your equilibrium expression, how to get your value for your equilibrium constant and what that tells us, how to solve for a rice or an ice chart, and making sure that we pay attention to the size of the vessel for each problem. This problem is unique to 400 degrees Celsius. And remember that the only thing that changes K is a change in temperature.